Hello. So today I'm gonna answer question 6 from a coordinated science paper 0654, summer 2019, variant 43. So this question is on physics, and it's about a lot of things, but it's a combination of pressure, refraction, waves, and a bit of nuclear physics. So I'm going to answer it one question at a time, and I'm going to discuss all the concepts that I used to answer it to help you revise. Okay, the first question is A. Figure 6.1 shows a penguin walking on the ice in Antarctica. The penguin has a weight of 25 newtons, and its feet have a total area of 22 centimeters squared. Calculate the pressure in Newton per meter squared exerted by the penguin on the ice when it's standing on both feet. Show your working. Now, since we're looking for pressure, we need to remember the formula for pressure. Remember that pressure is equal to force per unit area. Now remember that this area has to be perpendicular to where the force is acting. So we're given the force, which is the weight of the penguin, that's 25 Newton, and we're given the total area, which is 22 centimeters squared. Now you have to remember that it's in centimeters squared. We're going to ask for the pressure in Newton per meter squared. So we need to convert 22 centimeters squared to meter squared. So if we want to get the area in meters squared, we have to divide 22, okay, by 100 squared, and we should get 2.2 times 10 to the minus 3 meters squared. Okay, and so now we're gonna have to use the formula. So P is equal to the force, 25 newtons divided by 2.2 times 10 to the minus 3 meters squared, and we will get 11,000 Newton per meter squared. And so that's our answer for this question. Now for the next part, the penguin observes a fish swimming in a pool. Okay, shows a ray of light going from the fish to the penguin. The ray is refracted at the surface. The angles of incidence and refraction are shown. Calculate the refractive index and make sure that you show your working. Since this is a refraction question, we need to use the law that applies to refraction. We call that Snell's law. And it tells us that n sub 1 sine theta 1 is equal to n sub 2 sine theta 2. Okay, now as you can see, the light ray comes from the water to the penguin. So it's coming from a medium of higher optical density to a medium of lower optical density. That's why the light ray went farther away from the normal line. Now remember that when rays move from medium of higher refractive index n to a medium of lower refractive index, the ray moves away from the normal. Okay, which is observed in this situation. Now remember that this by convention, okay, we assume that the index of refraction of air is 1. Okay. Now in this case, our n sub 1 will be the one that we're looking for, which is this one here. That's n sub 1, and this is n sub 2, which is air. Theta 1 will be 30 degrees, and theta 2 will be 42. Now remember that the angle of incidence and the angle of refraction has to be the angle between the ray and the normal line. Okay, so if we're looking for n sub 1, we rearrange this equation to solve for n sub 1. N sub 1 is equal to n2 sine theta 2 over n sub 1. Over sine theta 1. Okay, and so we just plug in the numbers. So n sub 1 is equal to n sub 2 is 1, so it's just sine 42 degrees divided by sine 30 degrees, and the answer will be 1.3, because this is going to be 0.67 divided by 0.5, and that's 1.3. Okay, now take note that refractive index is unitless because it's a ratio of speeds. Remember that another formula for refractive index is c over v, where c is the speed of light, or for light at least, in vacuum, and v is speed of light in a material. So they're both speed, so that's why the refractive index is a unitless quantity. Now the penguin jumps into the pool of water and produces water waves. A 3-meter section of the pool is shown. Okay, show that the wavelength of the wave is 0.5. Now take note that looking at this is a transverse wave. And so to measure the wavelength of a transverse wave, we can do that using several ways, but you can do it from a crest to a crest, or a trough to a trough, or two identical points in a wave. Okay, now this whole train is 3 meters, but there's more than one wavelength in this. So you just have to count the number of wavelengths here, divide 3 by the number of wavelengths that you can see, and you'll get the wavelength of an individual wave. So let's start it. So that's one full cycle, another. So as you can see, it's repetitive. So you have 1, 2, 3, 4, 5, 6 complete cycles. So to get the wavelength lambda, it's basically 3 divided by 6 waves, and so we get 0.5. Yep, meters. All right. Now, the speed of the wave produced in the pool is 1.5 meters per second. Calculate the frequency of the wave. Now remember the formula that governs the relationship between the wave speed, the frequency, and the wavelength is V is equal to lambda F. Okay, where this is the wavelength, this is the frequency. Okay, so if we're looking for frequency, we just do F is equal to V over lambda, and since we're given the V, so it's 1.5 meters per second divided by lambda, which is 0.5 meters, and we get 3 hertz. So that means in 1 second, there will be 3 cycles in that wave. In the Antarctic, harmful ultraviolet radiation reaches the Earth's surface. State one danger to living things of being exposed to large quantities of ionizing radiation. So usually the answer to this is something related to cancer or mutation. So you can write it can cause, let me just write that better. Or cell mutation. Now, alpha particles and beta particles are both types of ionizing radiation. State two differences between alpha and beta particle. Let's just have a brief discussion about that. So, alpha particle let me write it properly. Okay, again, is just a helium nuclide. So you can write it this way, or He24. So you can see it has 4 nucleons, so 2 protons and 2 neutrons, and therefore it's positively charged. A beta particle, on the other hand, is just a high energy electron. Okay, so in symbol it will not have a nuclear number, but it has a -1, or it can be written as this. Okay, so as you can see, one obvious difference is their charge. Okay, alpha particle is positively charged, while beta is negatively charged. And also you can see that alpha particle will have a bigger mass. Okay, you can also say that alpha particle is more ionizing and less penetrating because it's heavier. Now, an isotope of an unknown element decays by beta emission to produce an isotope of silicon, which has a nuclear number of 28. Identify the unknown element and give its full nuclide notation. So a periodic table will be given in your exam. So, but essentially, what you're looking for is the parent nuclide in this case. Okay, so you're looking for the parent. That is your unknown. It's going to be here. Okay, and it yields, according to this question, produces an isotope of silicon with a nuclear number of 28. So silicon with the 28. Okay, plus the beta particle. So beta 0 minus 1. Let me just quickly Google what silicon's, silicon is 12. Oh no, silicon is 14. Okay, 14. Okay. So now basically this is just like a balancing of normal chemical equation. Right. Now since beta particle doesn't have a nuclear number for this to make sense, to be balanced, this should have a nuclear number of 28 as well. Okay, now if you look at this, this is 14 and a -1, so to follow the law of conservation of mass, this has to be 13. And if you refer to the periodic table, atomic number 13 is actually aluminium. So the correct answer here is aluminium with a nuclear number of 28 and a mass, and an atomic number of 13. That's how you answer this question. 13 marks all in all. Thank you.